Okay, we're live. I don't know if this is going to work. We'll find out. Oh, I still do my names. Let's see if I can find people again. Anybody there? Google Hangout on this computer.
Yes.
Oh, Kelly, are you there?
Yeah.
Hi. Awesome. I'm still waiting on a couple other people. I'm trying to get in a couple minutes.
Okay. Okay.
Is Apple TV? Just unplug it. Oh gosh. I'm gonna close all this. Hi, Lucy.
Hi.
When
I can hear her. This is so weird.
Did you guys put your questions pretty crazy, right? Doc, and we'll start hearing in that doc, or do you have other questions? Okay, my computer's kind of struggling with Wi-Fi. Nick, I just picked your question. I'm not really sure what I'm doing either. You're watching, but you're not actively, like, you're not in the video, which is totally fine. I think there should be for everybody like a question pane over on the right. Do you guys see that?
Is it the group chat?
Kind of, yeah. In a minute I'm gonna turn on screen share, and I'm just gonna be like writing on here so you can see me kind of work out problems. Can you guys hear me okay?
Yeah.
So what questions do you have?
Oh, okay. Well, I have one about the collision theory, and it's just like the nature of the reactants. How do you know, just like based on like what you have, if it's going to be a faster or slower reaction, or is it just like you can't really tell?
Know that that's just like one of the factors you would list. You wouldn't have to know anything specific of distinguishing between them.
Okay, got it.
I have a question about the lab.
Sure.
Okay, so one of the questions was asking like how which step would be the slowest. How are you supposed to figure that out?
Which step would be the slowest? So for the lab, what you want to look at is your overall reaction mechanism. Or sorry, your overall reaction rate. So you have like rate equals K times H2O2. Can you see what I'm typing on my screen?
Yeah.
Awesome. Okay. H2O2 to the first times Ki to the first. What were your orders?
Lab. Sure. Okay, so one of the questions was asking like how which step would be the slowest. How are you supposed to figure that out?
So it's based on your rate law equation. So like it gave you I didn't actually bring that home, so I don't have it in front of me. But it gave you a mechanism. Basically what you would go through is and say like, okay, if this first step was the slow step, then the rate would be K times, I think it was like H2O2 times HI. No.
I.
Times I, K, or yeah, I minus. And so if your rate law was this H2O2 to the first and Ki to the first, then that would match the first step being the slow step, because Ki is the same thing as I minus.
Okay.
If instead the second step was a slow step, then I think it'd be like rate is H2O2 times, what was it, like IO3 minus?
It was IO minus.
Was an intermediate, so you have to replace that with H2O2 and I minus, which made it in the previous step. Did I lose you on that?
I don't get the whole replacing thing.
Okay. So here's the deal. You can't have an intermediate in your rate law equation. Like anything that's in your rate law equation has to be part of your overall reaction. So if there's an intermediate, like so let's say your flow step was the one that gave you this, right?
Uh-huh.
Your flow step says the rate should be this, but IO3 is actually an intermediate. The rate actually wouldn't depend on the concentration of IO3 minus, because you wouldn't actually be able to measure that at any point, and you don't have that in data. You only know what you put into the reaction. And if the first step that makes the IO3 is a fast step, that means any stuff you put in to make it will immediately turn into IO3, enough to make it react with the H2O2 in the slow step. So you go back to your previous step that made the IO3, and you say, well, what went into making the IO3? In this case, it was H2O2 and I minus. So you replace IO3 with what made it.
Oh, okay.
And this would simplify into H2O2 squared times I minus.
Okay.
So pick the one that most closely matches your data. You may not have one that exactly matches, but just do the best you can.
Okay.
Hi, Jenna. I see your question. What other questions do we have? Hi, Amanda. I see you in here. Someone had posted in the doc I posted that they wanted to go over the 1997 B problem. So I'll do that one. Unless you guys who are here have questions. Any other questions? This is from the last page of the packet. C and E, and the short answer here. Oh, you know, it would have been good. It would have been good if I had that pulled up on my computer. I don't actually. So this is, I can do this on my phone. This is, ooh, hello. You guys are going to see all sorts of crazy stuff happening on my computer. Let me just minimize this for a minute. We can make it look better. Okay, so this is 1997B. In part C, it asks about the initial rate of change. So here, if it's asking you to find the initial rate of change, in this case it asks you about the rate of change of A in experiment 3. Looking back at the data you have for experiment 3, you know concentrations initially, and you know the initial rate of formation of C, and that table at the top. So here it's asking you to find initial rate, and one of the pieces of information that you have is initial rate of something else. So it probably means you're going to do those relative rates that we started with. So that was where you said like the overall rate is based on comparing the stoichiometry of the reaction. So rate equals, in this case, it would be -1/2 of the rate of A, which would equal, let's see, it would be just the negative the rate of B. And C has a coefficient of 1 as well, which would equal, so that would equal the rate of C. My pen is really struggling here, so it's probably not showing up real well for you guys. But in experiment 3, you were told that C had a rate of 5.3 times 10 to the negative third.
Mm-hmm.
So you plug that in for C. You can ignore B and D because the question isn't asking about them. But the rate of A is actually going to be twice as much as the rate of C because its coefficient is 2. So basically you could just say half of X is 5.3 times 10 to the negative third. It could be like 1 times 10 to the negative 2. Does that make sense? What other questions do you have?
For the integrated rate laws, it's like not on the review, but it's in the packet. You have the equation natural log of A equals natural log of A and then O minus KT. Where do you get that from?
That's actually going to be on the equation sheet that you get. It's derived from calculus. If you look on your equation sheets in the bottom left-hand corner, oh, see, I grabbed an old equation sheet. So not exactly the same one that you have. But you're going to be given that natural log equation and the second order equation with the 1 over A.
Oh, okay, gotcha.
You just need to know which one is the first order, which is second order, and you need to know the zero order one by memory because it's not on the sheet.
Okay. So is zero order just concentration of A equals negative K times T plus concentration of A initial?
Yes, I think so. I mean,
Okay.
let me think through this for a minute. It's like y equals mx plus b. And there's a chart of this in your book that would be good to look at.
Okay.
I can't remember what section that was in, but it had like the zero first, second order. It has the half-life equations in there for each of the orders. The only one you need to know how to use is the first order one.
Okay, gotcha.
For this one, let's see. So the concentration is your y value. So for a zero order, it would be the concentration of A equals, and then let's see, the slope is K and it's negative. So negative slope is K. And the x value is time. And the y-intercept is your initial concentration. So that would be a sub 0.
Okay.
And like I said, the other two would be given to you.
Okay. Thank you.
Mm-hmm. Let's see. So Jenna, I see you had a question there about going through a rate determining step problem. Let's see if I can find one. Anybody who's in the chat right now have one in mind? Rate determining step.
Are those the ones that we were doing after school today?
Yeah. Mm-hmm.
Okay.
I mean, it's kind of like the 1997 question part E, maybe?
Yeah, I was just looking at that one.
Okay, let me see if I can find that on my computer real fast, because that one would be good to look at. Hang with me for a minute here. You know what? I don't know. I think Mr. G made this worksheet, so I don't know if I have a copy of it. Oh, this is it. Yeah? Nope, this is a different one. 1997B. Oh, here we go. Okay. Is my screen showing? Am I doing this right?
I can't.
Oh, it's black.
Yeah.
Black. Uh-oh. Okay. If that happens, tell me. I'll try to fix it. I don't really know. Technical difficulties here. Hang with me. Whoop. Hi. I'm back on. Let's do... Oh, I know why, because we'll do a tire screen. That'll solve the problem. Kinetics problems. Okay, is it showing now?
Yeah.
Awesome. Okay. So the question that we were talking about was how can you do like a rate determining step kind of problem? And part E here says justify which one of these is consistent with the rate law you found in B. And in part B, you were supposed to find that the rate law equation would be first order for both of them. So it'd be like rate equals K times A to the first times B to the first. We want to know which of these mechanisms is consistent with that. So the way mechanisms work are that whatever the slow step is determines the rate. So with option 1, we would look at the slow step here, which is the second one. Mad, that's pretty funny. You would say that the rate equals K times M to the first times A to the first, because those are the two reactants in the slow step. However, what is M?
A plus B.
Yeah, it's an intermediate, right? Because it is not in our overall reaction. It's produced in the previous step. So you go back to that and you say, well, what made the M? It was actually A and B colliding with each other, which made C and M. So M would be replaced with A and B, because those are the two things that collided to make the M. So rewriting that, you'd have rate equals A times A to the second times B to the first, which is not consistent with what we found from experimental data. So number 1 is wrong. So you can do the same thing with number 2. Looking at the slow step here, it looks like the slow step is, again, rate equals A times M times A, but M is an intermediate. If you look at where it comes from, it's produced when B reacts. So we can replace the M with what makes it B. And actually, that one is consistent with our overall rate law that we found experimentally, A to the first and B to the first.
In number 1 for that example, does it matter that A plus B yields C also?
Not really, I don't think. It's
Okay.
And also, it's not at equilibrium, and typically it does need to be at equilibrium to do the replacing thing.
Okay.
That's kind of beyond the boundary of what you'd be expected to know on our test tomorrow, and I believe on the AP test.
Okay.
Just generally know the idea that if there's an intermediate, it can be replaced with whatever made it in the previous step. Let's see, what other questions do we have? Whoa.
Whoa, what's going on?
That's pretty crazy. We'll go back to this. That was hurting my eyes. Someone said number 19 on the multiple choice practice test. Don't worry about that so much. The question there was, which of the above shows a relationship between reaction time and reaction rate? Generally, what you should know about that, for number 19, let me see if I can pull that up. Here's practice kinetics questions. I think this has, no, that's old. I don't have a copy of that in front of me. Again, I probably should have thought about doing this electronically. But basically, just know that over time, the reaction rate slows because there's less and less reactants available. So over time, like as you move along your x-axis, the concentration will, the rate will slow down. So either graph A or graph B would be appropriate. This is number 19. You could basically say that as time happens, the rate decreases, and I don't care that you know that it's either linear or exponential. Hi, Grace.
Hello.
The last. Oops. What other questions did we talk about?
For number 21 on the same multiple choice, when it says which of the above shows reaction rate as a function of concentration, is that just talking about like the order?
Okay, so shows reaction rate as a function of concentration. So that means concentration here and rate here. So as you have more concentration of stuff, does the reaction go faster or slower?
Slower.
Well, greater concentration. Think about that video with the particles colliding that we talked about.
Yeah, faster.
The more concentrated it is, the faster the reaction is going to go.
Okay.
And that's why C was the right answer for that.
Okay.
Are there going to be a lot of conceptual questions on the test tomorrow?
There'll be a mix of conceptual and mathematical.
Okay.
Sorry, that's not a very helpful answer. But
It's okay. For number 6 on the multiple choice, are we going to be expected to do like a problem like that without our calculator?
Number 6. Here's the trick on that one. If you look at your equation sheet, the equation that they give you, this is number 6, right on number 6. The equation they give you is that no, they don't say natural log, they say like 0.693 over k equals t1/2.
Oh, so it would be like basically the same.
Yeah, so it's like the same number.
Okay.
That's how they get away with asking that kind of question on the multiple choice. Because, and in number 6, you just have 0.693 equals 6930. And so then it's just moving the decimal place.
Okay.
Let's see. Jenna said number 18 on the multiple choice. We'll pick that. Number 18. Okay, so it says on number 18, we have the reaction 2A plus B2, something. And the rate law is A to the second, B to the 0. It says which of the following is likely the rate determining step. So looking at the rate law equation, you see that B is not part of the rate law expression. So looking at your rate law equation, you say, oh, well, my slow step must have A reacting with A. So you don't look at the overall reaction for that, because remember, the overall reaction doesn't tell you anything about the mechanism or the rate determining step. You look at the rate law expression. Since it's A to the second, there's 2 A's in your reactant, which is what happens in option C. Options A, B, and D all have B as one of the reactants, and since B is 0 order, it must not show up in the rate determining step.
Do we have to know the threshold energy for the kinetic energy distribution charts?
Are you looking on that yellow sheet?
Yeah.
Here's what you should know about that. Basically, the activation energy doesn't change, right? So if this is your energy diagram, energy's over here, and like reaction progress is here. At a higher temperature, you don't change this graph. Increasing the temperature does not change the energy of the reactants or the products or the activation energy you need to get to. What it does is it makes the particles move faster. So when they collide, more of them are likely to have enough energy to overcome this barrier. So with the Maxwell-Boltzmann distribution, I don't remember what the axes are offhand. I think it's energy and number. At one temperature, the graph distribution might look like this, where most of the particles have this amount of energy, and if you heat it up, on average, each particle has a little bit more energy. And so if the activation energy, let's say, is 75 is here, at the lower temperature, only these particles have enough energy. But at a higher temperature, all of these particles have enough energy. So that's a fancy way of saying at higher temperatures, more particles have enough activation energy to react.
Okay.
So the only thing that can change an energy diagram is a catalyst.
Yes.
Okay.
Let's see. I see Nick had a question. Number 4 in the packet on integrated rate laws and half laws problem. Let's find that one. Oh my gosh, we did so many worksheets in this unit. I have like a mass of worksheets.
Are we supposed to turn in that like first worksheet that wasn't part of the packet?
I don't know. What do you think?
Nah, it's not part of the packet.
Wait, are you counting? Are you counting the last like pages that's the free response as part of the homework grade?
Yeah.
Okay.
I won't count that random first worksheet because I have a feeling a lot of people aren't going to know where that is tomorrow. It's important. And in an ideal world, I would collect it, but I will probably just collect that packet and look for about half of each worksheet to be done.
And then is the lab due tomorrow too?
No, Grace talked me into moving that back to Wednesday.
Oh,
Thank
great.
you,
Do that.
Grace.
It literally is causing me so much anxiety because everything went wrong in our lab.
Oh my gosh, yeah, Kelly, it was really bad.
Our lab was really bad too.
It happens. All you got to be able to do is do the calculations based on your data and then do your best to try to explain why that is.
Okay.
Okay, so we're going to go back to Nick's question from the integrated rate law packet worksheet. And this one's talking about sucrose. Let's see, you're told that the rate is first order. K equals C12H22O11. After 2.57 hours, the concentration drops from 0.55 molar to 0.45 molar. So what you want to notice is that it's first order. And then you'll want to use the equation from your sheet, which I believe, well, since it's first order, it's natural log. So natural log of A equals negative KT plus natural log of A initial. You just plug in the numbers that you're given. So initially the concentration was 0.55. And the natural log of your final concentration, that'd be natural log of 0.45. The K value you're not given, but since it's first order, you know that, wait, hold on, I'm looking at the wrong problem now. You're trying to find the rate constant, and you know time. It was 2.57 hours. So you can solve for K then. Looks like K would be 0.078, unless Mr. G made a math error on his answer key.
Oh no, that's what I got.
Per hour, because that was in units of hours. So basically, you just got to be able to recognize which equation to use if it's first or second order.
So we need to know the second order equation like that?
That one's also on the back of the equation sheet.
Oh,
you just
okay.
have to be able to recognize it. It's like 1 over.
Oh, yeah. Because it's like second order is 1 over the concentration, so then it's 1 over.
Yeah, exactly. This one's the first order. So they're not labeled, but the equations are on there.
Okay. Will we ever be asked about a half-life of a second order?
No. Mm-mm.
Oh, that's good.
Yeah. One less thing to worry about, right?
Yeah.
Okay, I have a question on number 4 for the multiple choice.
Mm-hmm.
I just don't understand like how you can tell what the intermediates are unless like they give you all of them.
Okay, so the multiple choice, number 4. Let's see. So you're trying to get the overall reaction 2NO and O2 and 2NO2. This is kind of like Hess's law in a way. You basically want to pick 2 of those options that add up to the overall reaction that you're going for there. And the second and the fourth one will do that. So the way I would have approached it is said, okay, well, kind of like in Hess's law, I know I want to end up with 2 NOs. Is that right? Is it the second and the fourth one?
Yeah, it is.
Yeah. Okay. Yeah. So if you look at that second one, this was kind of a tricky one because you had to like kind of sort through all of those NOs and 3s, and it's making my head spin right now to look at it. So by adding up those 2, you can see that this one would cancel. That would be an intermediate because it's a product and then a reactant. And then what's left, you'd have 2 NOs and an O2, making 2 NO2s.
Okay, so it's just like Hess's law and you have to see which ones cancel out.
Exactly, yeah.
Oh, I had a question on like the very first worksheet we were talking about at the very beginning. I kind of get like confused on the positive and the negative signs when you get your answer. Like I can get to the answer and everything, but like if it's a reactant, is it always going to be a negative rate?
Yeah, we kind of do some magic hand waving and just say, okay, if it's a reactant, it will have a negative rate or will be a decreasing rate. If it's a product, it'll be positive or increasing. As long as you like clarify that in your answer, or if the question sim says, what is the rate of decrease of this reactant? You could just answer with an absolute value. It would never be wrong, though, to include the negative on a reactant.
Okay.
Talking about like negatives and positives, can you go over like, I know this isn't this unit, but like we're gonna have to know it for the AP test. Can you go over like the work equation again? Like the, yeah, that one.
There's Q plus W. So this is a review. For anyone watching, this is not on tomorrow's test, but we'll do this real quick. So let's start with heat, Q. It's exothermic if heat leaves, and it's then negative. It's endothermic if heat goes in, it'll be positive. For work, if the system, if like what you're looking at does work, that's negative. If it does work, work will be negative. And if it has work done on it, then it's positive. Does that answer your question?
Yeah, thank you.
Okay. For integrated rate law about like the graphing, why is the slope always positive, even if like it says like negative k?
When you graph it, the slope isn't always positive, right?
Right.
But k always has to be a positive number.
Okay.
So if you graph it and you get a straight line, the slope is negative, but k has to be positive. You just make the slope negative, and that would tell you the value of k.
Oh, okay, got it.
If when you graph whatever, you get a positive slope, then slope equals k. And that's for second order.
Okay.
For 0 and first, the slope is negative k.
So K itself can never be negative. It's just
Correct.
a slope.
Correct. I want to get back to Jenna's question that she posted there. It was number 2 on the multiple choice. Pick that one. Number 2 on the multiple choice asks about comparing kind of how rate changes when you change the concentrations. This is number 2 on the multiple choice. A times A squared times B. And it says the concentration of A is reduced to half of its original value. So let's compare these two. To make the reaction occur at a rate of half of its original rate, I'm going to say I want half of my original rate equals K, and A, we want that to be half of what it was, half of the original A. And we want to know by what factor we have to change B. So I'm kind of like, I don't know if this is the purest way to do this, but this is just kind of like our rate law determination things. You can cancel out things that are the same on top and bottom. So basically then you'd have 1 over 1/2, that'd be 2, equals basically 1/4, because it's 1/2 squared times x. This is wow. I chose a really mathematical way to solve this problem. There's got to be an easier way to do this. And basically you want to solve for x then, so that'd be 4 over x equals 2, so that x would be 2. So you need to double the concentration of B. Maybe a more conceptual way to think about that would be that, let's say you want the rate to be 1/2 of what it was initially, and you know that you are cutting A's concentration in half, and you want to know how much you have to change B's by. By cutting A in half, that's actually going to be like a 1/4 because it's second order. 1/4 of what gives you 1/2 of the initial rate. So B would need to double, end up giving you the fraction that you needed. So basically you should be able to figure out, like, if you double one thing and you cut the other thing in half, how would the rate change? To answer Jenna's question here about rate determining step, do you treat the problem differently when there's a double arrow versus a single arrow? Not really for our purposes. Technically, if you're doing the replacement thing with the intermediates, you would need to have a double arrow to do the replacement. We haven't talked about what that means yet this year. So that's beyond what you would need to know at this point. Okay, what other questions do you have?
I have a question. Just okay. For the worksheet with the potential energy diagrams,
Yeah.
when it says what is the value of the activation energy of the uncatalyzed reaction, and then it says what is the potential energy, which one is which?
Do you know what number you're looking at?
Number 7 and 8. It just asks. It says what is the value of the activation energy, and then it says what is the potential energy of the activated complex.
Okay, so activation energy and activated complex are different things.
Okay.
That's the key difference here. So activation energy is the distance between the reactants, or wherever you're starting, and the peak.
Okay.
But the potential energy of the activated complex is the total energy from the base to the peak.
Okay.
Yeah. So activated complex is a point on the graph, just like the reactants and the products. The activation energy is a distance between the peak and where you started.
Okay.
Okay, so as the concentration, or as the reaction rate increases as the concentration increases, right?
Yes.
They're proportional. What are the other things that are proportional like that?
Temperature.
Yeah.
Okay, are those only two?
Let's see, factors.
Surface area.
Yeah.
Oh yeah, surface area. I forgot about that one.
Yeah, those are the biggies. We threw catalysts in that category.
Can we go over the types of catalysts?
Oh yeah.
Yeah, they're not really going to be on our test. They might show up on the AP test.
Okay, is it a new thing this year?
It is, yeah. I'm not entirely sure what they would ask. Acid-base, we're going to talk more about acid-base reactions in 2 units, so that'll make more sense then. Basically, they lose and gain protons to make the reaction happen faster. You've got the surface catalysts, and those are typically metals, and so they've just got a sea of electrons that you can steal electrons from, or gain electrons from, or donate them to. And then you've got enzymes, which are the biological catalysts that hold them in place. So I think primarily they wouldn't expect you to memorize something about them, but just kind of be familiar with the idea. If it said, this is a surface catalyst that allows electrons to move freely, how would it affect the activation energy? How would it affect this mechanism? And they could probably use those to pull in, because AP test likes to pull in multiple concepts to one question. So they might use an acid-base catalyst to tie together a kinetics question with an AP buffer acid-base question.
So you don't think we'll have to like draw a picture of them or anything?
No, I don't think so.
Okay, good.
What other questions do you have? None? Feeling ready? That's a good thing.
Is there anything that we did at the beginning of the unit that you think we might have forgot?
What we did at the beginning was the relative rate.
So that's just the using the coefficients of the thing, right? Like we did in class today, number C, or letter C?
Yeah. Mm-hmm.
Okay.
And then we talked about collision theory, the two factors. So not like the factors that make the reaction rate go faster, but kind of the why behind that, how you need the correct orientation and enough energy when they collide. Yeah, other than that, it should be pretty straightforward as long as you know like the integrated rate equations, which one goes with which order, and the graphs and which one goes with which order, and how to do rate law determination. There shouldn't be too many surprises.
And we don't have to use a graphing calculator, like you give us all the graphs?
Correct, yeah. I would give you the graphs and ask you to interpret them. What do you think will be the hardest part?
I think the multiple choice.
Yeah, I think so too.
Yeah, I had to think about that for a second. The multiple choice.
I think though, like all the calculations are pretty simple, but I'm worried for the multiple choice.
Yeah, there's always a few tricky questions about the concepts that if you think about it the wrong way, you'll kind of throw yourself for a loop.
There's nothing about the lab on the test, right?
Only in the sense that in the lab we're doing the same thing we were doing with the rate law determination, where you're comparing how changing the concentration affected the rate.
Okay. Do you have any other like true or false things like we did at the beginning of the unit? Do you remember that day that we went on the computers, like those true or false statements?
Oh, before we did mechanisms and catalysts, where I made up this and asked you to think about it?
Yeah, like any other like generalized statements like that?
Let me think for a minute. That was probably the most conceptual. I mean, false things about the factors that affect the rate, like a reaction will only occur when the particles, or a reaction will always occur if the particles collide with the right orientation.
So that's like that's false because they have to have the right speed too.
Correct, yeah. Mm-hmm. Yeah, if they just like gently touch each other at the correct orientation, no reaction will occur. They have to have both orientation and energy.
Okay.
Do we have to draw energy diagrams?
I mean, you should be able to. Like if I said that the reactants had an energy of 35 and the products had an energy of 15, and the activated complex had an energy of 75. You could say, okay, well, here's 35, that's my reactants. Here's 15, that's my products. Activated complex is 75. Does that mean that it is 75 higher than where you start, or that it's at the max of 75?
Max of 75.
Yeah. Ooh, hello. Yeah. So what would be the activation energy for this reaction?
40.
Yeah, the activation energy would be 40. What would be the delta H? That's the distance between the products and the reactants.
So 20.
It would be negative 20. And it's negative because the products are lower in energy than the reactants.
So you always do products minus reactants?
Yeah. And what about the activation energy for the reverse reaction?
60? Or no, 50, right? Wait, what's 75 minus 15?
Yeah. Yeah, you're starting at 15, you have to get up to 75. The difference there is 60.
Okay.
Okay, that makes sense. And then the potential energy is like just like the energy from like the bottom of the graph to like a point. So it's not.
Yeah.
Okay.
So you talk about the potential energy of the reactants or the activated complex or the products.
Okay.
You wouldn't have a potential energy of activation energy.
Okay.
The one on the multiple choice was like not right?
Oh yeah, that was
Okay.
all messed up. I don't know what was up with that.
Okay.
Units on K. You guys all know how to find units on K?
Mm-hmm.
That'll probably be worth a lot of points because it'll show up in multiple places. So it's the overall order minus 1 times whatever your time units are.
And the overall order, you just add them, right?
Yeah, you just add up the exponents.
And you want us to include that when we have K in the grade equation, right?
Yeah, so anytime you calculate K or put K into your equation, make sure you have those units in there. Yeah, I'm looking back through the bookwork now. Graphs, finding the orders. Yeah, it was a short unit, so there's not a lot of concepts.
Miss Eden,
Yeah.
can you go over 1991B for the A? I'm still confused on how you find the order if like the trials aren't the same.
1991B. This part?
The A, yeah.
A. Right, the rate law expression?
Yeah.
Okay, let me see if I can find that in the one I had open. I don't have that one in here. Let me look in the drive real quick. Any other questions? Any other questions while I'm looking for this? I think, Jenna, I think this test is easier than the last test, simply because most of it is review. We've done a lot of this from Honors Chem, so students typically do better on this than on the last one. The half-life equations, the only one you need to know is the first order one, and that's given on the test. You don't need to know anything about second or third. Or third. Third doesn't exist. Oh man, I'm getting tired. Second or zero order. Kinetics review. About this one? Oh no, that's that. I'm sorry, I don't have that exact question in front of me for the 1999 one. Was there a specific part you weren't sure about?
Yeah, I found the order for F2, but I was just confused on how you then find the order for ClO2 because there was like I did the part where you put them on top and then you cancel out K and you cancel out the one that's the same. But I don't know how you go back and find the other
For
reaction.
this one, oh yeah, okay. So I can go through that. So for this one, to find the order on ClO2, I compared experiments 1 and 3. So what you want to do is plug in what you know. So rate is K times ClO2 to some power we don't know times F2, and we know that it's to the first. And so we're going to compare that to different trials. So let's say we'll put 3 on top, 1 on bottom. 3 times ClO2 to the M times F2 to the first. And so then you just replace those. So rate in experiment 3 was 9.6 times 10 to the negative third. ClO2 in experiment 3 was 0.02, and F2 was 0.2. And then in experiment 1, the rate was 2.4 times 10 to the negative third, and ClO2 was 0.01, and F2 was 0.1. So that just got really messy. But basically anything that's on top and bottom can cancel. So the K's cancel. And then you combine like terms. So on the left, 9.6 divided by 2.4, that's 4. And then these are both to the m power. So 0.02 divided by 0.01, that's 2 to the m. And then 0.2 divided by 0.1, that's 2, and it's to the first power. So then you have 4 equals 2 to the m times 2. To divide both sides by 2, you got 2 equals 2 to the m. So the exponent there is 1.
Okay.
Basically just set up a ratio between 2 different trials and plug in all the numbers and the orders that you know.
Okay, thank you.
Okay, we maybe have time for like one more question. Any burning questions? Okay, make sure you get some sleep tonight. Don't stay up all night.
Thank you.
Yeah,
Thank
good luck.
you.
I'll see you guys bright and early tomorrow morning.